Well, hello there. Today's topic is going to be on thermal physics. It's the lesson one, it's a part one of the entire unit, and we would be focusing on the basics of thermal physics. So let's get started. The first thing I want to talk about is about temperature. So if my voice sounds a little loud, put the volume down. I'm a little too excited today. I don't know why. This is one of my favorite topics in physics. Um, Easy, no confusions, straightforward. So, okay, enough about me. Let's talk about temperature. So, temperature, so far you know that temperature is just a definition first, introduction here. So, it's a measure of degree of hotness or coldness of a body, how much heat is contained. It's not the measure of the heat. Heat is energy. This is a degree of hotness or coldness. We have known that it is measured in degrees Celsius or Fahrenheit. Now, a more standard unit, which is used all over the world by the physicists and also required for your A level exams, is Kelvin. Okay, or absolute temperature. Say, now the conversion factor is 273 degrees. So 27 degrees Celsius is nothing but 27 plus 273, that is 300 Kelvin. So 1 degree Celsius is 273, sorry, 0 degrees Celsius is 273 Kelvin. Okay, that's the conversion. So if you want to convert degrees Celsius to Kelvin, add 273. Let's try some. Let's convert first. Let's try and convert 10 degrees Celsius to Kelvin. Pause and do it yourself. Answer is 283 kelvins. If you have 20 degrees Celsius, or let's say minus 10 degrees Celsius, pause, do it yourself. If you've done, it is 263 Kelvin. So the lowest temperature is actually the lowest known recorded temperature is minus 273 degrees Celsius, which then becomes 0 Kelvin. So this is called absolute zero. Okay, so absolute zero is the temperature, is the lowest possible recorded temperature, theoretically, not recorded, theoretical temperature till date is absolute zero. So absolute zero is minus 273 degrees Celsius or 0 Kelvin. Now, the next thing that you've learned already in GCSE is the kinetic theory of matter. So what you need to know here is simple things. One is how the particles, so these, what you can see is a model of the particles of solids, particles of liquids, particle of gases. So you need to know two things: how these particles are arranged, the arrangement of the particles in solid, liquid, or gases. For example, this is, let's say, your screen. Okay, the particles of your screen are arranged very close to each other, so they are closely packed. So this is the arrangement of the particles of solids. For a gas, they are far apart. For solid, the movement is only vibrations at its own place. Okay, they do not move around. So you just need to know only this much. Two things: one about the arrangement, solids, liquids, and gases. Liquids, they are far a little bit away from each other and can move around. Gases, they are far apart, can move around with a larger speed. That's it. Now what you have more in this in A level physics is more kinetic model for gases, so that we do a little bit more in detail. Now before that, so this is kinetic theory model of it's a theoretical model of gases, but to understand that, first this, the Brownian motion. So Brownian motion is a motion, is a word that is used to describe the motion of the gas particles. So all of these are gas particles. So if you focus on any one particle, so that any one particle is shown by this red color dot here. So can you see how random the motion of that particle is? So that just tells you that the gas particles are always in random motion. Random means it can move in any direction every time it collides with the neighbor, neighboring particle. The direction of the motion changes. That's it. That's what Brownian motion is. Now, a typical question. Uh, Pause and read the question. Once you've done that, Brownian motion makes it possible to see the motion of air molecules. That's not right. Okay. It's caused by the collision of small particles. No. It's caused by collision between air molecules and small particles. That's the right one. So if I take this one, so this red particle, if it's a smoke particle, every time the smoke particle collides with the air particle, it's the Brownian motion. So typically Brownian motion is nothing, it's but the random motion of the gas particles. And how do we see it? By letting smoke get into a chamber, in a gas chamber, and see how the smoke particles are randomly changing their direction. Now, again, a topic that you've done in GCSE, internal energy. So quickly going faster. So this set of particles, this what you see on your screen, they are kind of like particles. So as you can see, they are very closely packed, so they must be resembling a solid, and they're vibrating at their own place. So this must be remembering a solid. Now, why? What kind of energy do they have? Because they're moving, they should have a kinetic energy. And because they are packed with each other, if you heat them, will the distance between the particle change? So that thing corresponds to potential energy. So internal energy of any system, your pen, your book, your own body, internal energy of your own body will be made up of the kinetic energy of the particles of your body and the potential energy of the particles. Now, what is the cause of these energies? What is the cause of Ke and what's the cause of Pe? Okay, both of them in combined forms the internal energy. So let's just see Ke. Okay, we know kinetic energy is because of motion. So if I'm considering, let's say, a block of ice, okay, I'm taking a block of ice here. This block of ice at minus 10 degrees Celsius, right? Now, this block of ice would have particles closely packed to each other, and these particles, why they are closely packed? Because of the intermolecular attraction, and they are vibrating at their own place. So they have a Ke because of motion and Pe because of intermolecular forces. Now, once I increase the temperature to, let's say, minus 5, minus 1, okay, I've heated it. So where is my heat energy gone? So what that heat energy is doing is making these particles vibrate faster. So they are faster vibrating. So they have increased the kinetic energy. But has the intermolecular distance changed? No. So Pe remains same. Okay, so let's do one by one. Ke is because of the motion of the particles of a body. Remember, we are seeing inside a body. And then Pe is because of intermolecular or interparticle, let's say particle, interparticle distance in a body. Okay, now what changes Ke? Ke is changed by temperature. Larger the temperature, larger would the particles move. Faster they move, more kinetic energy they would have. So kinetic energy is proportional to the temperature. Larger the temperature, Again, this temperature should be Kelvin temperature. Larger temperature, larger Ke. And according to Boltzmann law, okay, Boltzmann's law, you need to know that for your physics, A-level physics. Ke is half Kt, where K is Boltzmann constant. The value is in your equation sheet, and I'll tell you the value in a minute. So Boltzmann's constant, and T is the temperature in Kelvin. That means if I increase the temperature, my kinetic energy will also increase. Whose kinetic energy? Kinetic energy of the particles. Now, if I change, let me ask you a question. Yeah, let's see how focused you are. If I change the temperature from 10 degrees Celsius to 20 degrees Celsius, what have I done? Have I doubled the temperature? Answer is yes. Now, what would happen to the kinetic energy? Pause and think. What would happen to kinetic energy? Okay, so if you're thinking that the kinetic energy would be doubled, you're wrong. Why? Because we need to convert this temperature into Kelvin. So I will add 273. So this becomes 283 Kelvin to this one will become 293 Kelvin. So is the Kelvin temperature doubled? No, Kelvin is a capital K. Since the Kelvin temperature is not doubled, it has only increased. My kinetic energy will only increase, it will not be doubled. Do not make this mistake. You will have such exam questions where you might be tricked into believing this. Always convert your temperature into Kelvin. All right, so we got this. Okay, now the value of K. The value of K is 1.380649 10 to the power minus 23 joules per Kelvin. Okay, so the Boltzmann constant, I'm going to write it here. I'm going to take it up to 2 decimal places. You don't need to remember this. Joules per Kelvin. Remember, temperature is now in Kelvin. Now, specific heat capacity. Now, you've done this in GCSE again, but I'm still just going. So the Boltzmann constant is, as I've written on the screen, 1.38 times 10 to the power minus 23 joules per Kelvin. Now, specific heat capacity. I've done some scribbling here. So specific heat capacity is given by this formula, energy divided by mass times temperature change. Wait, let me just clear this screen. Give me a second. Okay, what do I do? How do I clear the screen? Discard. Okay, I think that's better. Yes. Okay, let's continue that. So specific heat capacity is the energy that is required to change the temperature, energy required to change the temperature of 1 kg of a substance by 1 degree Celsius. So delta T is change of temperature. Now, delta T here is change of temperature. This can be either in degree Celsius or in Kelvin. It does not matter. It would be same. I'll explain you how. Imagine if there is a 15 degree Celsius changes to 25 degrees Celsius. So what's change in Celsius? 10. But if I convert this into Kelvin, 15 plus 273 is 278, 288 Kelvin changes to 298 Kelvin. So the change of temperature is 10 Kelvin. So change of temperature, whether in Celsius or in Kelvin, is same. So it does not matter. in specific heat, whether you have the value in Celsius or in Kelvin, because the answer will still be the same. Now, what the specific heat capacity does, so whatever heat is given, so I'm just going to write mc delta T, rearranging this equation. You have that in your equation sheet. What is this energy capable of? This energy is capable of changing temperature. So whenever temperature changes, which internal energy changes? Kinetic energy increases. So now potential energy. So if I consider, let's say, going back to the same ice model, I have ice particles very close to each other and the temperature is 0 degrees Celsius. It changes to water. The particle goes little away from each other, but the temperature is still 0. It has done nothing but just changed state. Okay, so what happens? How did the state change happen? You must be giving some heat. So that heat that gives here, you've done this in GCSE, that heat is latent heat. So what does this heat do? The latent heat is the heat responsible for changing the state. So you have changed the state. So, but where is that heat gone? What energy has increased in the body when you were giving it latent heat? Is its PE, potential energy. If I increase the temperature of, if I want to boil this water, can I boil it at 0? No. I have to do what then? I have to increase its temperature to what? I have to increase it to 100. So which energy has increased? So when the temperature increases, which energy increases? So KE increases. So KE has increased. Now, if you give heat to it, it will change to steam at 100. So which energy has increased? Potential energy. So when the temperature changes, kinetic energy changes. When the distance between the particle or the state changes, its potential energy changes. Latent heat, which is the energy required to change the state of 1 kg of a substance. So divide by mass. Remember, so there's no temperature change in this equation, because when the state changes, there's no change in the temperature. This could be latent heat of vaporization when liquid changes to vapors, or latent heat of sublimation when solid changes to gas directly, or latent heat of fusion when solid changes to liquid. So names will not matter. What matters is you understand what is latent heat capable of doing. It is capable of changing potential energy of particles. That's what it does. Okay, let's just do this question then. Pause and do it yourself, but I'll be doing it. A continuous stream of water falls through a vertical distance. You know me, I always tell you the same thing. Draw the diagram. So the water is falling through a height of 100 meters. Assume no thermal energy is lost to the surroundings. The specific heat capacity of water is 4200 K. Force the temperature difference. So obviously the water is getting energy from somewhere. Who's giving that energy to the water? It's falling from some height, right? Whenever there's a height involved, which energy? So the gravitational potential energy is converted into heat energy, which is then mass times specific heat times temperature change. This is mgh. So mass cancels, taking g as 9.8 times 100, 4200 times temperature change. Now because it's a change of temperature, even if my options have Celsius, it would not matter because the change is same in Celsius or in Kelvin. Okay, I'm just opening my calculator to get this. So it's 980 divided by 40 to 100. So I am getting the answer as 0.2333333 up to infinity, and the answer is B. Voila. Okay, simple concepts from potential, gravitational potential energy, and specific heat capacity. All right, we got it. Okay, now this is what I would want you to do. Pause and explain what is happening to the temperature change with time. Okay, if you've done that, now listen what's happening here. So as the time is increasing, so this is something, you're giving heat to something because of which the temperature is changing first. So whenever there's a change of temperature, which energy is responsible for change in temperature? Go ahead, tell me. Well done. So specific heat capacity. So specific heat capacity, and which energy is then increasing Ke of particles. Brilliant. Now you're still giving the heat, but the temperature have stopped increasing, it remains constant. That means here state change, which energy you're giving? Latent heat. And increasing which? PE increases. Here again temperature change, so specific heat capacity increases Ke. What's happening here again? Again temperature is constant, PE increases because of the latent heat energy given to us body or whatever thing it is, and then again the temperature rise is happening, so Ke increases. Right, so that's just the basic of specific heat capacity and the latent heat. Here's a simple question. I want you to try it out yourself. Pause and try. I am just going to make the diagram. I'm going to go slowly. You can work with me also. So I have a 0.5 kg block of ice, minus 10 degrees Celsius. Then if it heated until it becomes steam, right? So if you heat it, it would first come to 0, still ice. Then it changes to water, but the temperature would not change. 0.5 kg, still 0 degrees Celsius. Then you have to give a lot of heat before it becomes 0.5 kg, but at 100 degrees Celsius. Then it changes to steam, 0.5 kg. Remember, whenever the state changes, do not change the temperature. See, water to steam, I've not changed the temperature. Ice to water, I've not changed the temperature. And then it has become now steam at 100, that's it. Now heat. Here, because the temperature is changing, I have to use mc delta T, 0.5. Whose heat capacity? Ice, which is 2100 joules per kg. Change of temperature is 10. Plus heat required here is ml, which is 0.5 times, what's the latent heat of fusion of ice? 3.3 times 10 to the power 5, plus here, what do you think? What's happening? Temperature change. So which formula? mc delta. mc delta T, 0.5. Now the specific heat of water, it has become water now, and temperature changes 100. Plus here state change ml, plus what is m? 0.5 times L is 2.26 times 10 to the power 6. Okay. Well, do we require the heat capacity of steam? No, we do not, because we are not changing the temperature of the steam. When we require the temperature change of steam, then we would use it. Okay. Okay. Let's just see. So 0.5 times 21. Oops. 0.5 times 21,000 plus 0.5 times 3.3 times 10 expel 5 plus, oops, no, I won't. Okay. Plus, if you are faster than me, then brilliant. Okay, 100 plus 0.5 times 2.26 times 10 to the power of 6 equal, I have 1515500. That's my answer. Okay, 1515500 joules. It's the energy. That's it. Okay, so understand that you are supposed to be calculating mc delta T when the specific heat capacity is required, and then you are supposed to be calculating, did I do any mistake here? Okay, let me just check my calculations. All right, so no mistake. Brilliant. So we got it. Okay, two things from today's video. One, specific heat capacity is to be used whenever there's a change in temperature, and whenever there's a change in temperature, there's an increase in kinetic energy. Latent heat is to be used whenever there's a change of state. When the state changes, the potential energy changes. And the standard unit for temperature is Kelvin. Absolute temperature, whenever you see the word absolute temperature, the temperature unit should be Kelvin. And change in Celsius is equal to change in Kelvin. That's it. Well done for watching the video. Keep learning. Bye-bye.